Hi, my name is Megan. I'm a Ph.D. student at Tyndall National Institute, and this is my poster on communication lasers using gallium arsenide materials. For data and telecommunication applications, lasers in the 1.3 to 1.55 micron wavelength range are most desired due to the low attenuation and dispersion they have when propagating through optical fibers. To achieve laser emission in this wavelength range, indium phosphide-based structures are generally used, but are not ideal due to substrate costs and restricted wafer size. In addition, the performance of the devices are affected by poor carrier confinement due to the small material bandgap offsets. Gallium arsenide-based lasers have been proposed as an alternative, mainly due to the ability to exploit lattice-matched aluminium-containing layers for better carrier and optical confinement. They also benefit from high-gain, compressively strained indium gallium arsenide quantum wells. This has all led to better performing devices at high temperatures. However, due to the limitations with the highly strained layers, the longest wavelength available to date for in-gas quantum well lasers is about 1.26 microns. To overcome this challenge, it has been proposed to grow a metamorphic buffer layer on top of the gallium arsenide substrate to confine and suppress the defects present due to the highly strained layers. This is done by employing strain relaxation. As the thickness of the metamorphic buffer layer increases, the indium concentration increases until it reaches a point where the in-plane lattice parameter is a constant value. This leads to the defects being confined to the bottom part of the grating, which can be seen from this TM image here. The next challenge was to optimize the laser cladding. It was found when first using ALIN gas and then using INGAP as the cladding layers with typical cladding thicknesses of 1400 nanometers. The surface morphology of the metamorphic buffer layer and the cladding layer was quite rough, with a root mean square value of 23 nanometers for ALIN gas and 34 nanometers for INGAP. To overcome this, a superlattice structure consisting of alternating layers of INGAP and ALIN-AS was used, and we can see that the root mean square value was reduced to 6 nanometers as a result of this. The cladding structure was also optimized by introducing ALIN gas grading ramps. This improved the bandgap offsets and thus the electrical performance of the devices. The third challenge was to optimize the quantum wells. The indium concentration and growth temperature was varied to prevent the formation of these 3D nanostructures on the surface. It was found that 40% indium concentration at a temperature growth of 580 degrees was the optimal parameters. Based on these epitaxial structures, a number of ridge-injected laser configurations with widths from 4 microns to 20 microns were fabricated. As a result of the optimized cladding structures, the turn-on voltage was recorded to be about 0.8 volts, while the resistance was about 4.5 ohms. The waveguide loss for a 20 micron wide, 300 micron long laser was calculated to be 30 per centimeter, with a quantum efficiency of around 57%. From the spectra here, it can be seen that the wavelength range was between 1350 to 1360 nanometers at 20 degrees, which is the longest wavelength recorded for a structure such as this. Down here, the devices were tested under continuous wave and pulse conditions. It was found that the characteristic temperature T0 for 4.5 micron wide ridge laser under CW conditions was 60 K. Under pulse conditions for a 20 micron wide laser, this was calculated to be greater than 100 K. This suggests that the cladding layers, while improving the electrical characteristics of the devices, were poor for thermal dissipation and as a result affected the performances of the devices under CW conditions. We have shown that gallium arsenide-based lasers can be extended to beyond the 1300 nanometer wavelengths with low threshold current density and excellent quantum efficiency. While there are thermal issues due to the superlattice cladding structures in these devices, metamorphic devices have the potential to be a suitable replacement for indium phosphide-based devices. Thank you for listening.